Xianming, you ready?
Yep.
Okay. Well, thank you all for attending the final webinar in the Sustainable Winter Road Operations webinar series presented by CESTiCC over the summer. The final presentation is the search for greener materials for winter road maintenance operations, being presented by Xianming Shi of the Washington State University Department of Civil and Environmental Engineering. Xianming is the site director for 2 Tier 1 university transportation centers. He also directs the newly established National Center for Transportation Infrastructure, Durability, and Life Extension, and serves as the Deputy Director for the WSU Strategic Research Initiative Stormwater Program. He has approximately 20 years of research and teaching experience in multidisciplinary topics, and he is a guiding force behind putting this webinar series together. So I urge you to pay close attention to what he says, and questions will be taken at the end of the presentation. And it's over to you, Xianming.
Great. Thank you, Vicky, and thank you everybody for spending the time. Again, this is the very last webinar for this webinar series, and I'd like to acknowledge the funding support by the 2 Tier 1 UTCs, CESTiCC for funding the research, and CAMC for funding some of my time preparing the talks. And again, the topic is the search for greener materials for winter road maintenance operations. In this one, we actually mostly focus on chemicals, or typically known as deicers. Of course, deicer is a very general term. We're referring to all the chemicals used for de-icing, anti-icing, or even pre-wetting operations. Just a sec here. So the talk will be mostly taken, from the chapter 17 of this new book, and also blended with some recently published research from my group. And just to refresh your memory, why is there a need for greener materials for snow and ice control operations? In the very first webinar, I mentioned there are multiple dimensions to this problem, and on the one side, we aim for better safety, mobility, and productivity of winter roadways. On the other hand, we also want to make sure we do a good job with environmental stewardship, minimizing the potential risk to vegetation, soil, water bodies, aquatic species, and other types of wildlife, and also minimize the potential damage to infrastructure such as reinforced concrete structures, steel bridges, concrete pavements, and asphalt pavements. Also minimize the corrosion risk to motor vehicles as well. So there are so many considerations in the decision making, but we try to do the best possible, taking a more balanced approach. So as we know, sustainable winter road operations rely on a number of factors, including the selection and proper execution of effective approaches under the prevailing conditions. This definitely includes the selection of the right type of de-icer materials. Again, de-icer could be the chemical for de-icing, anti-icing, and pre-wetting operations. So this webinar will start from a little bit introduction to refresh our memory why we're doing this, and then move on to an overview of recent advances in alternative de-icers and additives, followed by a holistic approach to materials selection or materials evaluation. Then 2 case studies of developing green liquid de-icer or anti-icer will be presented, and then I'll conclude with some remarks and acknowledgements. So to refresh our memory, the common de-icers out there being used on roadways, the most common one, of course, chloride salts, sodium chloride, magnesium chloride, or calcium chloride. The challenge with them is the potential risks to water bodies. For instance, they're highly soluble and highly mobile. Their intrusion or ingress into the surrounding environments also could mobilize heavy metals out of soil and vegetation. And also, what's really concerning over the long run is the conservative nature of these materials. because they don't degrade. They just move from one place to another, and it's really hard to remove. Now, a second type of deicers would be the non-creds, such as acetates, formates, glycols. These are typically used for airfield or aircraft anti-icing or de-icing operations. And also in recent years, the agricultural byproducts based or agro-based materials. The concern there is more of the short-term risk when they enter the environment. There's the potential of higher BOD, COD in the stormwater and causing oxygen depletion, and that's a concern. There's also some aquatic toxicity considerations or concerns. Another piece of this puzzle is the conventional additives. We tend to add corrosion inhibitors, surfactants, flame retardants, buffering agents, anti-caking agents. You know, there are many other types of materials we'll mention, but they also may pose some risk in terms of toxicity to the aquatic species. So that's the environmental risk. So that sort of, you know, demand us to look for better alternatives. And then there's another aspect, which is the potential risks of deicers to infrastructure. For instance, we talked about potential risk to cement concrete. You know, for instance, it's not just a physical process of accelerating, scaling, or freeze-thaw damage, but also there may be chemical reactions between the deicers and the aggregates and the cement paste. And also, in some cases, the deicers can chemically react with the asphalt binder, the aggregate, and the asphalt mixture. And once enough chloride penetrates through the protective concrete layer and get to the surface of rebar or dallbar, there's also the risk of active corrosion of the steel embedded inside the concrete. We're also concerned about the risk of, the corrosion risk of deicers to steel bridges or pavement markings and so on. So that's another dimension. More recently, we had some research demonstrating that, even in the case of sodium chloride, it's not just a physical interaction with the concrete. Actually, there's some calcium leaching and the formation of new crystals. In the case of potassium acetate, that's even more significant and caused significant reduction in compressor strength and split tensile strength and micro hardness. So in these cases, we demonstrate this calcium leaching out of the concrete and crystal formation inside the concrete, causing stress buildup inside concrete and eventually more severe cracking. Now, yet another piece is the risk or corrosion risk of deicers to vehicles. We also mentioned this in the first webinar. So that's another consideration. As we know, the Pacific Northwest Snow Fighters Association had previously established some test protocols or specifications, taken this corrosion concern very seriously. So in that context, we're looking at the recent advances in alternative deicers and additives. For one, the market is looking at some agricultural byproduct-based chemicals, either used alone as deicer or as additives in chloride salts. These are, this type of technology actually started around late 90s. And then we're talking about corn steep water, the cheese processing byproduct, also known as whey, wine processing byproduct, glucose, fructose, or even unrefined sugar. Of course, the sugar component would potentially stimulate the growth of microorganisms on the pavement and maybe even attract wildlife. So there's also the potential risk of strong odor. So in some cases, some patents are looking at desugared molasses so that they're biologically inactive. In general, this generation of agro-based chemicals tend to lower the ice melting temperature or increase the ice melting capacity. Some do both, some do one of the functions. And they tend to reduce corrosion to metals and improve the longevity on pavement and improve the UV absorption on pavement. So overall, it seems like they can do, they can enhance the performance of chloride salts. However, there are some concerns in terms of higher cost or quality control issues or toxicity to aquatic systems, especially when introducing organic contents into the surrounding environment. Now, more recent advances are looking at degrading some of these organics to lower molecular weight carbohydrates and then blend them with some inorganic salts or freezing point depressants. For instance, some degradation is using the polysaccharides derived from corn, wheat, barley, or oats, sugarcane or sugar beet, or some filtering of the condensed solubles from breweries. Also, another group of technologies looking at oxidation to produce carboxylic acid, which are stronger or more effective corrosion inhibitors at lower concentrations. Because one challenge with traditional agro-based chemicals is that you need a significant content, say 3% or 5% or even 20%. In those cases, there's a risk of diluting the ability of ice melting, and they're not very effective corrosion inhibitors, because corrosion inhibitor by definition should not significantly dilute the other constituents. Now, other groups of non-chlorides include potassium or sodium acetate or formate, glycol-based products. Again, these are potentially useful, but we cannot allow too high a dosage in the formulation because of the oxygen demand issue. Also, in recent years, there's the increased interest in formates and succinates. These tend to have lower BOD or biological oxygen demand than the acetates or glycol. Now, if we look at beyond the freezing point depressants, there's also a group of other additives. For instance, for corrosion inhibition or corrosion inhibitors, traditional corrosion inhibitors used for other industries are chromate-based, and they're very toxic. So over the last few decades, the industries have moved away from chromates and trying to look for non-toxic oxyanions. Now, these are typically containing atoms of oxygen, sulfate, phosphate, or nitrogen. So, for instance, I list the groups here in terms of organic corrosion inhibitors, such as molybdates or thioglycolates or phosphonates. An interesting one is also triethanolamine, which is actually used in concrete industry as a strength enhancer, but it's also an effective corrosion inhibitor. Now, inorganic corrosion inhibitors may include phosphates, borates, and silicates. And again, in a later case study, we tested, sodium metasilicate. And then yet another group is rare earth metal salts. Now, what about other options? Here's another one, which is the agro-based byproducts. Again, like we mentioned earlier, some of the byproducts tend to not only enhance ice melting performance, but also reduce corrosion. So one recent example was published in SCE. We used a zero waste process to chemically and then biologically degrade sugar beet leaves to derive green chemicals, and they seem to significantly reduce the corrosivity of magnesium chloride to metals. And then there's a more comprehensive review in this reference, if anybody's interested, in all the corrosion inhibitors out there on the market or recent advances. Now, we talked about the sugar beet leaves, but also the same technology was used by us to derive green chemicals out of peony leaves. And in this case, we also demonstrate they are very effective corrosion inhibitors. The corrosion inhibition, of course, is around 70%, not 90 or 95%, but considering the low cost of this material, and it's also a waste utilization process. There's no liquid or solid waste produced from the process. It's a natural fermentation process, and we use some chemical tools such as FTIR or free transformation infrared spectroscopy to characterize what kind of chemical groups are in them, and used LCMS liquid chromatography mass spectroscopy. Basically, we identify the effective components in them. Again, it's a mixture of things, mostly organic amines or phosphates. So yet another feedstock we played with was the skin of apple, or the waste of apple after the industry has taken the useful or edible parts. So again, this process produced a very effective corrosion inhibitor. Actually, after 2 weeks of testing in the lab, basically the corrosion inhibition reached around 90%, actually 98%. So we also studied the science behind it, and looks like what's working is really this organic phosphate. It tends to serve multiple functions. For instance, it makes the metal surface more hydrophobic, and also make the rust denser, and therefore protect further corrosion attack. And beyond corrosion inhibitors, there are other additives for enhancing the performance or as melting capacity and other properties. So in the book chapter, we look at the patterns or publications of the last decade or so. We found a few very interesting ones, like the use of radiation absorber, which tends to be a lower concentration, of course, no more than 1,000 ppm. But in these cases, it tends to absorb UV light and thermal energy from the environment, and therefore enhance the deicer performance. And also, oftentimes, there's a mixing of inorganic freezing point depressants and organic ones, because the inorganic freezing point depressants tend to have higher ionic strength due to their lower molecular weight. So given the same concentration, they have higher ionic strength. But for the organic ones, they tend to offer stronger hydrogen bonding. For instance, the use of low molecular weight polyols. And there are other types of additives for various applications. For instance, in the case of anti-icing, the use of thickeners or polysaccharides. And these are typically for airport or aircraft applications, but they may trickle down to the highway industry. Some other cases, the use of wetting agent or surfactant, such as organophosphates. Again, in the sugar beet leaf extract, we also detect the presence of such compounds. And if the agro-based product is stored for a long time, we also need to add antioxidants to ensure longer storage stability. So there are also techniques available, such as the use of potassium or sodium sorbates and the sodium azide. Again, there are other techniques, especially for solids, like you need anti-caking. In other cases, when we have, for instance, the use of metasilicate, we may need also a pH buffering agent and so on. And sometimes we use anti-spalling agent to make sure the deicer risk to the concrete is minimized. So depending on the customer priority, different formulations could be developed. So there are a lot of products on the market, but how do we select them? Right now, of course, mostly we're looking at effective temperature, the initial cost, but there's more to this equation, as we know. So we're advocating a balanced perspective, basically collectively examining the direct cost, performance parameters, and the potential risks associated with implementing the various products. So one case study we presented was from the lab. We had 4 hypothetical scenarios. For instance, we're trying to produce a liquid brine blend using a corrosion inhibitor, sodium chloride, and also calcium chloride. So if we want to consider mostly the cost, we put decision weight of cost as 10 and the other considerations as 1. Or if we consider we're really concerned about effects, then we put the effects such as corrosion of metals and effect on concrete as 10, others on 1. So, and so on and so forth. And the number 4 is a balanced approach. We basically consider everything almost equally important. So that was actually based on a real survey of DOT staff. So we came up with the decision weights. So in that scenario, we try to optimize the formulation accordingly. So if we're looking at a cost first approach, you can see that we end up using the least amount of inhibitor and the least amount of calcium chloride. So the blue, light blue over there give us the highest composite index if we have a weighted average of every dimension. So this is a cost first approach. Now, if we switch to the balanced approach, then the optimum is shifted towards something that has a reasonably or relatively higher inhibitor dosage and higher calcium chloride dosage. So depending on the user priorities, the optimum could shift. Now, a more complex scenario is the use of analytical hierarchy process, or AHP, to define the decision weights. So basically, the survey process would ask the input of the practitioners in terms of which dimension, such as cost or concrete damage or asphalt damage or whatever, and then ask them to rank them. So depending on the relative importance, we come up with decision weights. So in that case, we can have a relatively scientific process or systematic process to decide decision weights. And this was illustrated in this other paper, where basically we demonstrate using the balanced approach or the actual priorities from the DOT survey respondents, then most naturally sourced liquid deicers tend to rank higher if we look at the final composite index. And actually, we'll get into the AHP process a little bit later in the case study. Now, here's another case where we look at a number of different products, salt brine, magnesium chloride, and other solid salts from Idaho Transportation Department, and then look at the environmental risks based on literature, and then rank them, normalize the risk between 0 and 100. So we have different values for different products. But again, these are from the literature values, not from the actual testing, because actual testing would be almost cost prohibitive. Now, we also look at performance or cost aspect and risk to infrastructure. Again, normalize everything between 0 and 100, and we came up with a evaluation matrix. And in the end, the ultimate goal is to multiply this table with the decision weight table and come up with the final composite index for every product. So in this case, we found if you look at the final column here, the composite index range between 41 to 65. So a perfect deicer would be 100. So one of the solid salts ranked 65. Again, this is a demonstration of how to incorporate some lab testing results and literature review values with user priorities. In yet another study, we had a little bit better luck. So some of the products ranked 67. But again, this is based on the specific priorities by the agency. So in other words, these values could shift depending on what the priorities are. So there are certainly a few caveats in the quantitative analysis. For instance, there's always discrepancy inherent in extending data from the lab testing to the field, or from field studies in other regions to Idaho. And also there's a lack of reliable correlation between the lab results, evaluating the performance versus the field data. On the risk, very similar situation, the lab test methods may not reflect the field scenarios, because the field scenarios are very diverse, seasonal, site-specific, and stochastic. So we argue that additional data would be desirable to enable sensitivity analysis and validate some of the calculations for each product of interest. And also, in reality, oftentimes, a maintenance agency may not rely on a single product. Depending on the road weather scenario, maybe preferably a toolbox approach is used. So this kind of decision matrix or composite index is really just a tool to help the initial screening of things. Now, if we move on to two of the case studies, the first one was from Alaska. We had a project with Alaska Department of Transportation and Public Facilities, and they produce almost a little more than 500,000 gallons of salt brine every year, and use about 55,000 gallons of additives. One of them is Boost, to basically boost performance of salt brine to enable them work under colder temperatures, because the shipping of magnesium chloride from out of state or the lower 49 would be too expensive. So the project aimed to develop green liquid deicers so that we can offer the DOT with more options, especially with locally available solid salts and some other additives, especially waste materials. So the process is that first we identify some waste materials or byproducts and then try to blend them with sodium chloride and design experiments to optimize the formulation based on the user-defined priorities. So in the end, of course, it should shift towards field operational test and implementation. So in this lab study, we used the differential scanning calorimetry and identified a few interesting products, such as the distillery waste from a process of using barley to produce vodka. So they have two types of liquid waste. One is known as head, one is known as tail, and they seem to have some ice melting properties. And then we blend that with a trace amount of acetate, succinate, and urea. And also we used the electrochemical impedance spectroscopy, or EIS, to identify promising additives for corrosion inhibition. So end up with these two, potassium gluconate and sodium metasilicate. So with the DSC, we identified that there are a few interesting mixes. We basically had a statistical design experiment. So one of the winners is mix 3. You can see that the dashed line is the sodium chloride. We can see that the initial freezing point temperature, or phase transition of water to ice, happens around -5 Celsius. And once we move on to mix 3, that basically moved that temperature, also known as characteristic temperature, to near -10. So that's a desirable feature. In this one, you see that we reduced the use of sodium chloride from 23% to 20%, but we used some liquid waste, 7% head, 5% tail, with some other additives. So the number of mixes, but I want to highlight this one, mix 3. You can see the ice melting performance at 30 degrees Fahrenheit is much better than the control, which is the 23% sodium chloride brine. So it's actually, I didn't show the data here, but it basically reached the level similar to 30% magnesium chloride. Now at 15 degrees, very similar trend. Mix 3 was much better than the salt brine control. And at 20 degrees, in this case, we actually compared not just to the salt brine, but to the product they tend to use for colder temperature. At 20 degrees, they basically blend salt brine with Boost at 80 to 20 volume ratio. Their challenge was the Boost additive was a relatively expensive commercial additive. So blending at 20% significantly increased the cost of the liquid deicer. So in this case, we could potentially replace that brine blend with mix 3. As you can see, the performance is still much better. We actually tested significantly better in terms of the p-value in statistical terms. Now, one thing we did detect was a decline of performance in some liquid formulations because of evaporation of this head and tail. So we further experiment with other additives, for instance, the use of urea. Basically, it's kind of hard to see here, but the best one had had a stable performance over time because of the use of urea and other additives. But I want to have a mix 13Z because later on we tested more of that. In this case, we actually bumped the sodium chloride concentration back to 23% and used 2% urea, and the performance was much better than the sodium chloride boost blend. And we also tested the corrosion to carbon steel. And again, following the Pacific Northwest Snow Fighters Association test protocol, the mix 3 was much less corrosive to carbon steel than the salt brine. Actually, many other products had the same feature. Now, in terms of impact on concrete, we followed a sharp freeze-thaw test in the presence of diluted liquid deicer. Everything is diluted 3 to 100 by volume. In this case, you can see the mix 3A, which actually blended with, instead of 20% sodium chloride, we used some magnesium chloride, and the scaling loss was much less. However, at the time of that study, we didn't realize the potential problem with this magnesium chloride, because if we follow the sharp test, as you can see, magnesium chloride was given the least mass loss. So the surface of the concrete was perfectly fine. However, if we look at the more recent study, also from my group, we found out actually there's some internal damage without surface distress or scaling. So in other words, the blending of salt brine with magnesium chloride should be carefully tested. One thing that would give us a better handle on the issue is instead of relying on mass loss or scaling loss, we should also test tensile strength or compressor strength. So in this case, you can see the mix 13Z is having a little bit better residual strength than the one exposed to 23% sodium chloride. And this one actually had 2% urea. So to summarize, this case study demonstrated the feasibility of developing a series of sustainable liquid formulations tailored to meet the varying requirements of winter maintenance operations, depending on whether you're looking at 15 degrees, 20 degrees, or 30 degrees, whether or not you're more concerned about concrete scaling or loss of strength or corrosion to steel bridges, your optimum formulation may be different. And the use of local vodka distillery waste offers a cost-effective alternative to high-cost proprietary products. Actually, in some of the formulations, we end up using, say, 3% boost instead of 20%. Of course, in many others, we use 0% boost, so that will reduce the cost. And of course, there is a need to further study. If we want to do actual implementation, we need to test the oxygen demand, the permanent friction with field operational tests, and maybe even test the use of such materials for pre-wetting operations. If we end up using them in the toolbox, we also need to develop application guidelines, basically how much is optimum under different weather scenarios. Now, that concludes our first case study. The second one is also recently published. In this case, the feedstock we used, or the waste we used, was sugar beet leaves. Previously we mentioned some of the products on the market use desugared molasses or even sugar beet juice. In those cases, the organic content is pretty high. So we aim to further reduce that organic content by breaking down the organics using a biological and chemical process. So we characterize these products using FTR and LCMS and some of the tools, and we test the asperging performance and friction on the anti-iced pavement. Actually, in this case, we use this deicer for anti-icing operations. We also validate the COD, BOD values are acceptable. So in this case, again, there's a statistical design experiments. How do we do this? I guess is to use the uniform design table so that we can use the limited number of experiments to explore a large domain of unknown variables and interactions. And again, in this case, the main constituents we used were dandelion leaf extract, sugar beet leaf extract, metasilicate, sodium formate, and sodium chloride, and the rest is water. And we use some of these tools to identify what kind of chemicals in them. As you can see that these chemicals tend to have a molecular weight, no more than 1,000, and they contain a lot of organic phosphate or nitrate or oxyanions. So two different types of feedstock, dandelion versus sugar beet. Of course, the chemical products or green chemicals are different. And we tested the different mixes with the 23% sodium chloride. You can see, statistically speaking, we identified 4 mixes in this green box, which had much higher ice melting capacity than the salt brine control, which is in the pink box at 25 degrees Fahrenheit. Now, if we look at impact on cement mortar, starting from mass loss, again, statistically speaking, there are a number of products or mixed designs that feature much less scaling loss. And we also did some multi-regression analysis. Turns out the beneficial constituent to protect the cement mortar is the sugar beet leaf extract. The p-value is 0.12, is not as good as less than 0.05. Because typically when we define whether or not something is statistically significant, we say p-value less than 0.05. But again, considering the experimental results, this basically gives us roughly 88% confidence that the sugar beet leaf extract was protecting the cement mortar. And these are consistent with the literature that the organic amines and phosphates tend to be beneficial to the free salt durability of mortars or cement concretes. Now, we also look at the compressor strength. The difference was not significantly, not statistically significant, but we still see that some of the mixes have better or higher residual compressor strength after the salt scaling test. And the most beneficial constituent was the sodium metasilicate. The p-value is less than 0.05. And also we look at the potential risk to thermal cracking of asphalt mixture. One test is to look at the use of bending beam rheometer or BBR, which gives us 2 numbers. One is the stiffness value. The higher the stiffness value, usually the worse. Also means the higher thermal stress, which means at colder temperature that asphalt mixture tends to crack. So again, there's no statistical significance between the blue box and the pink one, but there are a number of them actually have worse impacts on asphalt mixture. However, if we look at the left group in terms of M value, the higher the M value, the better ability to relax the stresses. So many of them actually, statistically speaking, have better ability to relax the stresses compared with the salt brine. Now, if we look at the potential corrosivity to metals, all the mixed designs have lower corrosion risk to carbon steel. And the beneficial constituents statistically analyzed are these. The most important one is sodium metasilicate, and the dandelion extract was also beneficial. So was the sodium formate. Now, armed with all these pieces of information, what we do is using a decision-making process, again, AHP or analytical hierarchy process. So what we do is, you can see this table, we list out the different dimensions of this problem. Like our interest was having good ice melting capacity at 20 minutes or 60 minutes, and also looking at the lower corrosion rate, the lower mass loss, and asphalt stiffness, and so on. So we basically give a relative importance ranking. And then we based on the table above, we come up with decision weights. and then we summarize them. We end up with each parameter we have decision weight at the very top of this. So when we look back the 16 mixed designs versus the control, we can then basically multiply the decision weight table with the actual experimental data and come up with a composite design, so composite index. Of course, before we do that, the experiment data was normalized between 0 to 100 for every parameter. So in this case, we end up mixed design being the best formulation with a score of 92 out of 100, which means really good balanced performance and impacts. We look at control, which is ranked 14 out of 100. So we further study the performance of this mixed one versus the salt brine control. For antiacid at 25 degrees Fahrenheit, 30 gallons per lane mile in the lab, we demonstrate the friction coefficient is significantly better with the one antiacid by mix 1. So p-value less than 0.05. And also we test the shear strength of the snow bonding to pavement. And there's a little bit lower bond strength with the mix 1 antiacid pavement, which means it's beneficial. Again, in this case, the p-value is not as good as 0.05, but it still gives us roughly 82% confidence that mix 1 is better in terms of anti-icing. We also look at the eutectic phase diagram. The orange one is the traditional sodium chloride or rock salt, and the mix 1 gives us basically a lower eutectic temperature at 25% as its eutectic concentration. And we also tested the chemical oxygen demand, or COD, and BOD in the lab. And these values definitely higher than sodium chloride because we have organic contents in them, but they are much lower than the maximum level of COD and BOD allowed by the World Health Organization for an effluent to irrigation channels. Because for World Health Organization, their maximum level allowed was COD 300 milligram per liter and BOD 100 milligram per liter. So to summarize, this case study demonstrates a viable solution to diverting agro waste to green anti-icing formulations with with balanced properties and reduced impacts on natural environment. And mix 1 features relatively low risk to engineering properties of Portland cement mortar and asphalt binder, while being effective in improving friction coefficient and with relatively low BOD, COD values. So the future work should further enhance the process to extract the green chemicals, since we know which ones are the effective compounds now. Then depending on the specific user priorities, we can optimize or redefine the optimum formulation. To conclude this webinar, we briefly reviewed the recent advances in alternative deicers and additives. In general, it shows a paradigm shift towards sustainability, more or increased awareness or interest in green chemicals. Also, we had demonstrated research to establish a framework that enables collaborative and data-driven decision making, whether it's selecting or formulating deicers. This is done by integrating agency priorities with data either from lab testing or field testing or from literature. Certainly, we mentioned there are caveats, but that's the first step towards the right direction. Currently, there are considerable data gaps in quantifying deicer performance and impacts for decision making. New R&D are focused on improving the performance and reducing the negative impacts of liquid formulations, often enabled by the use of agro-based chemicals, non-chlorides, and commercial additives. Again, the key is that the balance between the performance and risks. To acknowledge, of course, my team and collaborators and the the funding agencies over the last decade, NSF and the 2 Tier 1 UTCs, Clear Roads, Washington State DOT, and also there's a lot of media coverage about the green chemicals. With that, I welcome your questions. Thank you.
Hi, Xianming. There's one question that's been posted by somebody who does not have a microphone. And the question is, how many tons of sugar beet leaf extract would you need to support 8 million gallons of Nacl brine? And how many acres of sugar beet plants?
That's a very good question. So in other words, we're not trying to, replace everything with sugar beet extract. We're just demonstrating the possibility of using agro waste. Now, so this is pretty much a regional question. If the region has that industry and they see the opportunity to divert that waste towards a liquid additive, then they can do it. But I haven't done the calculations. So in other words, this basically demonstrates a possibility on the technology side, not so much market analysis per se.
All right. If anybody else has a question, please feel free to raise your hand and I'll unmute your microphone. Or I can read aloud any questions that get written into the question box if you don't have a microphone.
Actually, Vicky, I also want to add that the same process, basically more like a platform technology, we demonstrate we can use different waste, like the sugar beet leaves, like the dandelion, like even Kentucky bluegrass, apple pomace, and many, many other things. So they all give some beneficial results in terms of enhancing performance in ice melting and reducing corrosion. But of course, depending on the specific scenario, that's more to be optimized. We didn't go that far because this type of UTC research is more exploring high risk, high return possibilities.
All right. So anyone have any other questions? Any follow-up? All right. Well, thank you very much, Xianming, for your time, and thank you everybody for attending this webinar. And I hope that you have gotten value out of the presentation. And at